A Portland Community College Mathematics Telecourse. A course in Arithmetic Review, produced at Portland Community College. Because of all of the previous lessons, this is an easy one. Remember that percent means 8% in this case, means 8 per 100, percent. And just by saying it and writing it mathematically, it is changed to a fraction right then and there. Then it's just a matter of reducing, in this case dividing top and bottom by 4. For most percents, it's just that simple. Remember that percent means per 100. Write it and you have your fraction. Now sometimes it's not quite that simple because you'll have decimals and fractions tied up in this part right here as well as a whole number. So in that case, perhaps it's better if we say this in a rather cut and dried rule. To change a percent to a fraction, first drop the percent symbol. So redoing this problem, if we dropped the percent symbol, I would have simply 8. Then change to a fraction. 8 as a fraction would be 8 over 1. Then third, multiply by 100th. So multiplying by 100th, and in this case, because we're multiplying, I can use the reduction or cancellation law. 4 goes into here 2, 4 goes into here 25, 2 times 1 is 2, 1 times 25 is 25, and I'm done, and it checks. Then, of course, reduce, which in this case we reduced before we multiplied. Now, actually in this case, this method of saying percent, writing per 100 is easier. But these rules will be handy when this portion here gets to be messy. So drop the percent, change to a fraction, multiply by 100, reduce. Let's apply those rules to a few fractions or percents. Drop the percent, change to a fraction, multiply by 100th, reduce. In multiplication, you can reduce actually before you multiply. 10 goes into those two, 2 goes into here 6, 2 goes into here 5, 6 times 1 is 6, 1 times 5 is 5, done. Now they might also instruct for us to change this fraction to a mixed number, and of course that would be 1 and 1/5. But this is the fraction. This is not. This is the mixed number. Another example. Now see, because of that decimal point, this is beginning to get a little bit messier. But if I were to drop the percent and then change to a fraction, this would be 82 tenths. To remember our trick for that, forget this for a moment. We said way back, pretend like the decimal isn't there, that's 82, right over 1, then add 1 0 for each decimal place. Do you recall that? Then multiply by 100th. And there's a lot of reducing that can be done there. 2 goes into here, 41. 2 goes into here or here. I'll take it into here. That is a prime number, so I can't divide it anymore by anything other than itself. So 41 times 1 over 5 times 100 is 500. 41 500ths is what this percent is equal to as a fraction. Now let's do that one once again by a peculiar shortcut that a few teachers like to teach. Listen to this, and if it strikes you and you can remember, use it. Otherwise, go back to the basic rules we gave you just a moment ago. But this peculiar shortcut is this. Pretend like that decimal point isn't there. Write it as a fraction, so that would be 82 over 1. Then give it 1 0 for each decimal place, and then 2 zeros to account for the fact that I have a percent. Then reduce that, and you would get the same thing. Pretend like the decimal isn't there. Change that to a fraction. Then 1 0 for each decimal place, then 2 zeros for the percent, and you have the fraction. By the way, that always works. And reduce it, and you have the reduced fraction. Let's try the next couple of problems by both methods, the standard method and this peculiar shortcut. Now the standard method, drop the percent, change to a fraction, but now that would be an improper fraction. So that would be 42, and 2 is 44 sevenths. Then multiply times 100. Now let's do the same thing by our shortcut before we finish this, and you'll see why the shortcut works. The shortcut says pretend like the decimal isn't there. Well, it isn't there in the first place. Okay, now change this to a fraction, and you would get 44 sevenths again. Then you would add 1 0 for each decimal place, there isn't any, and 2 zeros for the percent. And see, this right here is 44 700ths. So you indeed get the same results. This is where the 2 zeros come from. It's from the times 100th, which is what percent means. And then, of course, reduce. 4 goes into 44 11 times, and 4 goes into 700 175 times. So my reduced fraction is 11 175. Okay, now if we were to divide this, change it to a decimal with a fraction to the right place, then change that to a percent, we're right back here. Now here's sort of a granddaddy of all problems. It has fractions, decimals, and percent all in one problem. So when we say to change to a fraction, that means we don't want the decimal point or the percent point. We somehow want both of these out, but still know that our answer is equivalent in value to this number. Here's a case where the shortcut works very nice. Pretend like the decimal point isn't there, and we have 3 times 5 is 15, carry the 1, 9, 10, add 2, gives me 107 on top, thirds on the bottom. That times that plus that. Then our shortcut said to append 1 0 for each decimal place, and there's only one, and then 2 zeros for the percent, and then reduce. And as it turns out, that's already reduced. Okay, once again, pretend like the decimal point isn't there, change to a fraction, which would be 107 thirds. 1 0 for each decimal place, 2 zeros for the percent, and you have your fractions, and then see if it can be reduced. A nice shortcut, very effective. Now please note, another way of looking at those series of rules or steps we gave you is simply to remember that the mark percent can always be replaced by times 100th. And it's very important that you have this times as part of it. And sometimes this is easier to remember than those 3 rules that we gave you. So if you have a problem like this, you could have simply 46, and we have simply stated that the percent may be replaced by times 1/100th. And of course, to make 46 into a fraction so that you can perform the multiplication, you have that. And then of course you can reduce before you multiply. 2 goes into this 23 times, 2 goes into this 50, and I get 23/50ths. Isn't that nice? All from just this one simple statement, that a percent can always be replaced by times 1/100th if that's what you want to do. And of course, see, we've ended up with a pure fraction, which was our goal, starting with a percent. Let's do another one. Let's change this to a fraction. Now here again, don't be misled. This says change to a fraction. You might want to say, well, gee, I already have a fraction. What's to change? But it's really the percent that they want to get rid of. So what they're really trying to say is, I want a pure fraction. That is, I'm trying to get away from the percent. But this statement we just had simply says, if you've got a percent, you can replace it by times 1/100th, and that is a fraction, isn't it? So remember, this is when you're trying to get to a pure fraction, is when this is most helpful. However, technically, this is always true under any condition. So I have 1 2/3. And the percent I can be replaced by 1/100th. So what am I doing? I am multiplying a mixed number times a fraction. So we change the mixed number to improper fraction, which would be 5/3 times 1/100th. And then because I'm multiplying, I look for cancellations. And I finally get 1/60th. So the pure fraction 1/60th is equivalent to 1 2/3%. They're just the same quantity, just written differently. And so of course, they certainly look quite different. And this can erroneously lead people into believing that they are different. And they're not. They're the same number, just written differently. So again, that's a very valuable thing to remember, particularly later when we get into some verbal or story problems. Let's do a couple more just to drive that point home. Our rule is that the percent can always be replaced by times 1/100th. Now this doesn't mean you always do it. It just means you may always do it if you wish. So in this case, let's see what happens. We have 0.8, that's that part right there, and the percent is being replaced by times 1/100th. But now if we're going to multiply, let's at least get both of them as pure fractions. So the 8/10 as a pure fraction is this, times 1/100th. And then we cancel wherever possible. So 2 goes into here 4, 2 goes into here 5, 4 goes into here once, 4 goes into here 25, until finally I have 1 times 1 on top, and 5 times 125. So the pure fraction, 125th, and this decimal each represent the same value, just written differently. Now let's again check our ballpark thinking here. This is certainly less than 1%, and 1% is 100th. So this number should be less than 100th, and this number is indeed quite a bit less than 100th. So at least they are reasonably of the same size. All of that from remembering this simple sentence that percent can be replaced by times, important to remember the times, 1/100th. Again, another one. This may simply be lifted off and replaced by times 1/100th. But this is 1 3/10, which is an improper fraction. That becomes 13, that is a mixed number, which becomes 13/10 as an improper fraction, which now gives me the form to more easily multiply. There is no reducing that can take place, so I get 13/1000 is equivalent to this percent representation. Now let's use this fact right here in a slightly different form to show that it also explains problems we've done in previous lessons. There, this is the same percent we had in a previous problem, but instead of changing it to a pure fraction, we now want to change that percent to a decimal. In fact, a pure decimal. Then let's go back to our note where we said that this may always be replaced by times 1/100th, but reminding ourselves that 1/100th could also have been written as 0.01, and of course there's the times. So when we say that a percent may be replaced by times 1/100th, we mean by times 1/100th whichever way you wish to express it, either as a fraction or as a decimal for when we're trying to get to a pure decimal. So in this problem, since we want to get to a pure decimal, I will replace this percent by times 0.01. Then if we multiply these two, we would get 0.013. You can multiply it and double check it. And see, this verifies that the shortcut rule we had back a lesson ago, or 2 lessons ago, actually is logically firm. It holds water. See, in this case, the rule was if we want to get away from a percent, we drop the percent and move the decimal point 2 places away, inserting placeholder zeros if necessary. And of course, we get the same results, which we well should. It's the same problem, just looked at with different logic. And perhaps this simple logic might appeal to you where the other rules didn't. So you see, we're giving you 2 or 3 ways of logically looking at the same problem so that you can adopt for your own memory whichever seems to fit your mode of thinking the best. So let's use our remaining few moments to review solving proportions once again. So if you are indeed quite good at this process, you may want once again to leave this lesson and go back to your homework. But if you're not super smooth at solving proportions, again, watch this few minutes, because we will soon be upon a set of story problems where if you're not good, really good at solving proportions and reasonably good at percent decimal fractions conversions, the story problem just isn't going to be possible. So within our last few reviews, we've been looking at this from 3 different angles. Let's do it once again, because there'll come a time when we'll want to use each of those viewpoints. The most basic approach to proportion was to remember the simple rule that we take the top times the bottom, and again just show the multiplication. So R times 75, set it equal to this bottom times this top, and again just show it. 7 times 225. So once again, top times bottom. set equal to bottom times top. Then finally, divide both sides of that resulting equation by the multiplier of the unknown wherever it is. And of course it cancels out here, isolating the unknown, which is what we mean by solving in algebra. And the reason we didn't do the multiplication but just showed it, because it might happen that there is cancellations that can be done, which would save us a lot of work. So in this case we can see that 25 goes into 75 3 times, and 25 goes into 225 9 times, and again 3 goes into here once, 3 goes into here 3, and I'm left with 7 times 3, which is 21, which was fairly fast. So once again, be sure that you have memorized this simple approach, top times bottom, set equal to bottom times top. Then divide both sides by the multiplier of the unknown. That, in effect, solves the problem for us, wins the game. What's left is simply the arithmetic, and we simply do what it's telling us to do. So this was our most basic approach to solving proportions without the use of a calculator. However, if one has the use of a calculator, as you would certainly hope to have with a problem as messy as this one, you do the same thing, but you do your thinking not on paper but all mentally, and your arithmetic on calculator. So recall there we concentrate on the fact that we have two diagonals, so we search first to find the diagonal without the variable, and you multiply those two numbers. So 5.389 times 9.057. Then you go to the other diagonal, which does have the variable, and you divide by the number on that diagonal. So divide by 7.248, and we will have solved for our variable, which is called m here. As soon as we punch the equal, which is 6.734 to the nearest thousands. The digit before that is less than 4, so I round down, so it's 6.734. And again, we mentioned the calculator is so fast that always when you're finished, very quickly redo the problem. So 5.389 times 9.057 divided by 7.248 equals, and verify that your first answer was correct. The calculator is certainly fast, but there's always a chance of punching wrong buttons or a button not hard enough without realizing it. So actually, the chances for errors increase on calculators over hand work. But the calculator is so fast that you can redo it 2 or 3 times even if necessary to double check yourself. In practice, you will use a calculator as more than any other technique. However, we reminded you that there are times when you will work with fractions and you want to stay with fractions and not the calculator decimals. But we also pointed out you do exactly the same thing here as you would have done on the calculator, but you do it with fractions. So again, to solve for the k, we would scan for the two diagonals, find the diagonals without the variable. We're going to multiply those, then we're going to divide by this. But knowing that we're going to multiply and divide fractions, we change everything to improper or pure fractions. So this one would become 13/5. This one would become 21/4. And this one, of course, is 3/1. So now we're going to multiply these two. See the diagonal that doesn't have the letter. But again, we indicated that you just show the multiplication. Don't do your work until we've got the whole thing set up, because then there might be shortcuts we wouldn't see otherwise. Then we're going to divide by the number on the diagonal with the letter, but we remember, dividing by a fraction is the same thing as multiplying times its reciprocal. Now that it's all set up and we see that we are multiplying, we have permission to cancel wherever possible. And in this case, there's just one cancellation here. Then multiplying what's left on top, 4 times 13 is 52. And on the bottom, 35. And we have our reduced answer. If we want it as a mixed number, this is 52 divided by 35. And we can see that goes in once. And the remainder is 5 from 12 is 7. 3 from 4 is 1 out of 35. So this proportion is true if k had the value of 1 and 17/35. So you see the 3 different kinds of reviews that we did. First, the most basic approach, top times bottom set equal to bottom times top. Then divide both sides by the multiplier of the unknown. Finish the arithmetic, and you're done. The second portion is doing essentially the same thing with a calculator now, but now finding 2 diagonals, multiplying the numbers on the diagonal without the variable, then dividing by the number on the diagonal with the letter. And of course doing it all on the calculator and rounding off from the calculator. Then in this last procedure, doing exactly the same thing except with fractions and changing all our fractions to pure fractions, or if you would, improper fractions, then setting up what we're going to do before we do it so that we can look for our last-minute cancellations to save ourselves some arithmetic. So you see, really that's very, very simple, isn't it? However, as simple as it is, it's going to prove to be a tool that will help us to do many, many business story problems involving percents. But by that time, it's not enough that you can do this in a struggling manner. That will hurt you, not help you. You must be clean and smooth at this. So as we go through our reviews, if you find that it's not clean and smooth yet, that means you still have time to do some practice before we get to those story problems. So do listen to this and do review if you need it. And if not, of course, you know you have some easy work ahead of you. Again, this is your host, Bob Fennell, wishing you the very best of logic.